They once called it the most unsettling idea in all of physics, not black holes or time travel, but this: two particles, created together, sent to opposite sides of the universe, and somehow they stay connected. For example, just imagine flipping a coin here on Earth, and someone flipping a matching coin on Mars at the same time, and every time yours lands heads, theirs lands tails, without fail. No interference, just perfect coordination across space. That's not science fiction. That's quantum entanglement. It's real, it's been tested, and it's freaking weird. But here's the part nobody wants to say out loud. Just because it works doesn't mean we understand it, or even know what it is. Because this thing, the way it connects particles instantly across space, breaks almost everything we thought we knew about how reality works. So what is it really? Some glitch in the math? A trick of the measurement? Or is the universe built on something way stranger than we ever imagined? Because if entanglement is real, then maybe nothing is truly separate, not even us. Quantum entanglement sounds like something ripped straight out of science fiction. You take two particles, split them apart, send them to opposite ends of the galaxy, and somehow they still act like they're one. Do something to one, and the other instantly responds. No signal, no delay, just connection, as if the universe itself forgot to draw a line between them. Einstein hated that idea. He called it spooky action at a distance, and he didn't mean that in a good way. To him, this wasn't science, it was superstition, a glitch in the math, a sign that quantum physics, for all its clever equations, must be missing something important. Because how could the universe, a place supposedly ruled by the speed of light and clear, local cause and effect, allow for something like this? For decades, that question hung in the air like a challenge. Scientists debated it. Philosophers argued over it. The equations kept working, but no one could really explain what was going on. Was this just a weird coincidence we didn't fully understand? A math trick? Or was it a clue, pointing to something deeper, something stranger, something that might rewrite our entire picture of reality? That's where things start to get interesting, because today, quantum entanglement isn't just an abstract thought experiment. It's not just a weird corner of physics people argue about in conference rooms. It's becoming real, real enough to build things with, real enough to power the foundations of next-generation quantum computers, real enough to encrypt information in a way that's physically impossible to hack, real enough that we've started seeing its fingerprints in experiments happening in labs, in satellites, even in outer space. And yet, there's still this lingering doubt, because if you stop and think about it, it doesn't feel real, does it? We're told that the speed of light is the ultimate limit, that the universe follows rules, that things over here can't affect things over there without something traveling between them. That's the classical view of reality, the one most of us grow up believing. But entanglement breaks that in half. It doesn't just bend the rules, it tears them wide open. So here's the real question at the heart of all this. Just because something works, just because we can measure it, even use it, does that make it real? Or are we looking at something so fundamentally strange that our very idea of real needs to change? In this video, we're going to follow that question all the way down the rabbit hole, from Einstein's objections to experiments that shattered expectations, from early doubts to quantum computers and encrypted satellites, from spooky coincidences to the possibility that maybe, just maybe, everything is connected in a way we're only beginning to understand. Because this isn't just about particles, it's about the structure of reality itself, and whether the world we think we live in is anything like what's actually out there. Let's be real. Quantum entanglement sounds like it shouldn't exist. It breaks every rule we've used to make sense of the universe. Since Newton, we've believed that the world runs on logic. Things happen in order. Causes lead to effects. Information moves from one place to another through some kind of signal. Nothing just happens out of nowhere. But entanglement throws all that out the window. Picture this. You flip a coin in New York. At the exact same moment, someone else flips a coin in Tokyo. There's no connection between you, no signal, no trick. And yet somehow, every time you get heads, they get tails. Every time. No exceptions. It's like the coins are whispering to each other across the world, but faster than light and without saying a word. That's basically what happens with entangled particles. You measure one, and the other instantly knows how to behave, even if they're separated by light years. Not because they're sending messages, and not because they were pre-programmed. They just respond together, instantly. And that should be impossible. Every instinct we have says that things need to touch, to interact, to be connected by something. But with entanglement, there's no connection, at least not one we can see. This has left physicists with a brutal dilemma. Either everything we thought we knew about space, time, and causality is wrong, or quantum entanglement isn't real, just a weird illusion caused by bad data or missing information. And for a long time, that was the debate. Is it real, or just a misunderstanding of the math? Because if it is real, then reality is way stranger and more connected than we ever imagined. The origin of the weirdness. Let's rewind to the early 1900s. It was a time when the world made sense, at least according to classical physics. The universe was thought to be like a giant machine, predictable, rational, built on laws that worked like clockwork. Newton's laws had stood for over 2 centuries, and they explained almost everything. Planets orbiting stars, cannonballs flying through the air, tides rising and falling. If you knew where something was and how fast it was moving, you could predict what it would do next. No surprises, no mysteries, just cause and effect, playing out across the cosmos. But there was a crack forming under all that certainty. A quiet revolution was brewing, not in the stars, but in the tiniest places imaginable. Scientists began looking closer at atoms, and what they found didn't fit the old rules. The deeper they looked, the more things started to unravel. At the atomic scale, particles didn't behave like little billiard balls as Newton would have imagined. They behaved more like waves, like smeared out clouds of possibility. They weren't always where you thought they'd be. Sometimes they weren't anywhere at all. This wasn't just a small error or an exception to the rule. It was a whole new world with its own set of laws. A world where certainty didn't exist, where randomness ruled, and where observation didn't just reveal what was there, it decided it. Take electrons, for example. In the classical world, if you shoot an object through a pair of slits, say, 2 holes in a wall, you expect it to go through one or the other. Pretty straightforward. But when scientists fired electrons through 2 slits at once, something bizarre happened. The electrons didn't just go through one slit or the other. They created an interference pattern, like ripples in water. That's not something particles are supposed to do. It's something waves do. Even stranger, when scientists set up detectors to watch which slit the electron went through, the interference pattern vanished. The electrons started behaving like particles again, as if they knew they were being watched. It was as if reality itself changed, depending on whether someone was looking. This wasn't just unexpected, it was deeply unsettling. It forced scientists to rethink the very nature of matter. Was an electron a particle, a wave, something in between? The best answer they could come up with was both, and neither. This is where the concept of the wave function came in. Instead of thinking about particles as having a specific position and speed, quantum mechanics described them as a set of probabilities, a cloud of possible outcomes. The wave function told you where the particle might be, but not where it was, because until you measured it, there was no definite answer. That's hard to wrap your head around. Imagine flipping a coin and having it spin in the air, but instead of being heads or tails, it becomes a mix of both, a weird blur of possibilities. And then, the moment your eyes land on it, it snaps into a definite state, heads or tails, but not before. Before that, it exists in a kind of in-between. This wasn't just theory. The math worked. The experiments backed it up. But it defied everything we thought we understood about reality. It said that the act of measuring something could change it, that particles didn't have definite properties until they were observed, that nature, at its most fundamental level, was built on uncertainty. And then, things got even weirder. Out of this strange new world came something no one expected: entanglement. At first, it sounded harmless, just another curious feature of this quantum reality. But it would soon turn out to be one of the most disturbing and fascinating ideas in all of science. Here's the basic idea. Take two particles, say two electrons, have them interact in a certain way, and they become entangled. That means their properties are now linked. Measure the spin of one, and you instantly know the spin of the other. No big deal, right? But now separate them. Put one in your lab, and send the other one to the other side of the planet, or across the solar system, or 1 billion light years away. Doesn't matter. The moment you measure one, the other reacts instantly. No signal, no delay, no way for one to send a message to the other. And yet, they stay in perfect sync. That's what spooked Einstein. To him, it sounded like magic, or worse, nonsense. He called it spooky action at a distance. And who could blame him? Everything we knew about the universe, everything he himself had helped build, said that nothing travels faster than light. And yet, here was something happening instantly, across any distance. It broke the rules. It didn't care about space or time. It suggested that two things, once connected, never really become separate. This was not how reality was supposed to work. But according to quantum mechanics, entanglement wasn't just a strange side effect. It was a core feature, part of the operating system, a natural consequence of the way the universe handles information. In the world of particles and probabilities, it's not just about where things are or how fast they're moving. It's about how they're related, and relationships in this world are everything. Two particles can become entangled through a shared event, like being created from the same source or interacting in a particular way. After that, they stop being individual objects. They become one shared system. You can't describe one without talking about the other. That alone is wild. But what's even crazier is how far this goes. Because when scientists tried to explain this using classical physics, it didn't work. You couldn't say there was a hidden message being sent between the particles. That would still require some kind of signal, and that signal would need time to travel. But entangled particles respond instantly. It's like they're sharing a brain, like the distance between them doesn't even matter. This led some to think maybe space isn't what we think it is. Maybe separation is an illusion. Maybe, deep down, everything is connected in ways we can't see. At the time, most people didn't know what to do with this. Some dismissed it, others argued about it. A few leaned into the madness and said, okay, what if this is just how reality works? That's when the weirdness became more than just weird. It became real. The math made precise predictions. The experiments matched. Again and again, physicists found that entangled particles behave just like the theory said they would. And yet, the idea itself remained deeply uncomfortable, because it forces you to let go of something we're all trained to believe, that the world is made of separate things, that if you cut something in half, you get two pieces, that one object can't affect another unless they touch, or at least send some kind of signal. Entanglement says otherwise. It says the universe isn't made of parts, it's made of relationships. Even if you separate two particles by light years, their connection remains. They act like one system. Their destinies are tied, and no one fully knows why. It's like the universe has a memory. This didn't come from science fiction. It came from hard math and harder experiments, from labs filled with lasers and detectors, photons and electrons dancing under the rules of a strange, invisible game. A game that doesn't care about our common sense or our expectations. A game that's been running underneath reality this whole time. Quantum mechanics didn't just add a few strange ideas to science. It forced us to question the foundation. It revealed a world that's not deterministic, but probabilistic, not made of things, but of possibilities. And entanglement sits at the heart of it, proof that reality is far more connected, far more delicate, and far more mysterious than anyone imagined. That's the origin of the weirdness. Not just particles behaving strangely, but a total shift in how we think about what's real. And the weirdest part? We've only just begun to understand it. Einstein's spooky problem. Albert Einstein didn't like it. Not just a little. Not just as a quiet disagreement over lunch with colleagues. He really didn't like what quantum physics was saying. Because the deeper physicists dug into this strange new theory, the more it seemed to ignore the very things Einstein believed made the universe understandable. Causality, logic, distance, time, and worst of all, certainty. See, Einstein had spent his whole life thinking the universe was built like a giant clock, an enormous orderly machine. If you knew the position and speed of everything, you could predict the future. Not just roughly, exactly. You could, in theory, rewind or fast-forward the universe like a movie and never miss a frame. But quantum mechanics laughed at that idea. Instead, it told us, particles don't have exact positions until you measure them. They don't have exact speeds either. In fact, they don't even exist in one specific state until you interact with them. Before that, they're just clouds of probability, waves of potential, both here and there, doing everything and nothing until you force them to choose. This wasn't just weird, it was offensive, to Einstein at least. And then came the worst part, the thing that truly made his skin crawl. Entanglement. This bizarre idea said that two particles, once linked, once part of the same system, could be separated by any distance, and yet still stay connected. Measure one, and the other responds instantly, not quickly, not within a reasonable delay, instantly, as if space didn't matter at all. If this was true, then the entire structure of space and time, everything relativity had shown us, was under threat. It was like discovering that you could send a whisper from one end of the universe to the other without anything moving in between. No signal, no particles exchanged, just poof, instant coordination. To Einstein, this wasn't just puzzling, it was an existential threat to physics. He didn't think the theory was mysterious, he thought it was wrong, so he set out to prove it. It's 1935. Einstein's in his mid-50s, already a legend. He's changed the world once with special relativity, and again with general relativity. His equations explain gravity, the bending of space-time, the motion of planets, the expansion of the universe itself. But this quantum stuff, it feels like a bad dream, a hack job. It works, sure, the math predicts results, but the interpretation, it's chaos dressed up as science. So he reaches out to two other physicists, Boris Podolsky and Nathan Rosen. Together they write a paper with a long, boring title, Can Quantum Mechanical Description of Physical Reality Be Considered Complete? But hidden behind that dry headline is a bold, almost rebellious idea. They set up a thought experiment. No labs, no lasers, just logic. They imagine a pair of particles created together, linked in some quantum way. According to quantum theory, these two particles are now entangled. Their properties are no longer separate. They're part of a single system, even if you send them flying in opposite directions. Now, if you measure the position of one, the position of the other becomes instantly known. Same with momentum. You don't even have to touch the second particle. You just know what its properties must be, based on what you saw from the first one. Sounds magical. But here's the twist. According to Heisenberg's uncertainty principle, you can't know both the position and momentum of a single particle with perfect accuracy. So what happens when you measure position on one particle and momentum on the other? You've somehow learned both things, without ever violating the uncertainty principle directly. To Einstein, this was the smoking gun. He argued, If you can predict something about a particle without disturbing it, that information must have existed before the measurement. Otherwise, how could the particle know what result to give? And if that's true, if the particle has real properties before you measure them, then quantum mechanics is missing something. It's incomplete. There must be hidden variables, information we just haven't discovered yet, that determine what those measurements will be. In his view, quantum theory was like describing a coin toss without ever mentioning the weight, air resistance, or how hard you flipped it. Sure, you can say it has a 50% chance of landing heads, but that doesn't mean the outcome is random. It just means you don't know all the factors. He believed the same was true for particles. We just didn't know enough. But that didn't mean the world was probabilistic. It only looked that way. This is important. Einstein wasn't being stubborn. He wasn't just refusing to accept a new idea out of pride. He genuinely believed that nature had to be logical at its core. That physics wasn't just about describing what we see. It was about uncovering the deep, hidden laws that make it all work. And this quantum business, it felt like a magic trick. It gave the right answers, but it didn't explain what was really happening underneath. To him, quantum mechanics was like knowing how to use a TV remote without understanding how the electronics inside work. Sure, you can change the channel, but unless you know what's happening under the hood, you don't really understand the machine. And this spooky action at a distance, that broke the machine altogether. Because if entanglement is real, if two particles can coordinate their behavior instantly across any distance, then it means the world isn't local. And locality is a big deal. It's the idea that stuff can only affect stuff nearby. That to change something far away, you have to send a signal, a force, a particle. That cause comes before effect, and everything follows a chain of events, step by step. Take that away, and suddenly the universe stops being a sequence and starts being a web. Einstein couldn't accept that. He refused to believe that particles had no reality until someone looked. He thought this whole idea, that measurement creates the universe, was absurd. He once said, with frustration, "Do you really believe the moon isn't there when you aren't looking at it?" But here's the twist. Einstein didn't deny the math of quantum theory. He knew it worked. He just thought it was incomplete. A placeholder, a surface-level model, waiting to be replaced by something deeper, something that would one day bring sanity back to physics. He wasn't trying to prove quantum mechanics was right. He was trying to break it. And in the EPR paradox, he thought he had. He believed they'd shown a contradiction, that quantum mechanics couldn't be both correct and complete. Either the particles were influencing each other faster than light, which breaks relativity, or the particles had hidden properties from the start, which quantum theory said they didn't. Pick your poison. But the quantum physicists of the time, they didn't see it that way. Bohr, Schrödinger, Heisenberg, they leaned in. They said, maybe this is just how the universe works. Maybe it doesn't care about your common sense. Maybe it doesn't care about distance or speed or what we think should be possible. Maybe reality is probabilistic. Maybe observation does play a role. Maybe particles don't have properties until we measure them. And maybe, just maybe, Einstein's resistance wasn't the defense of truth, but the last gasp of an old worldview trying to survive in a stranger one. In the end, Einstein's spooky problem didn't go away. It just got harder to ignore. The questions he raised would linger for decades, until someone finally found a way to test them, not just on paper, but in the real world. And that is where the story takes a turn. Because in the years that followed, physicists would run the tests. They'd check the math, and they'd discover that the universe might be far more connected than even Einstein was willing to believe. But for a moment in history, he stood firm, defending logic, defending locality, trying to save the universe from becoming spooky. And in doing so, he may have helped uncover the very thing he feared most, a universe where everything is entangled. Niels Bohr's radical view, Niels Bohr didn't just disagree with Einstein, he lived on a different wavelength entirely. Where Einstein saw confusion, Bohr saw clarity. Where Einstein saw a broken theory, Bohr saw the birth of a new kind of reality, one that didn't follow our old rules and didn't care much for our need to make sense of it. See, when quantum mechanics started to rise, it wasn't just tweaking a few equations, it was turning physics inside out. Up until that point, science had been built on this idea that the universe runs like a clock. Everything happens for a reason. Every cause has an effect. If you know all the variables, you can predict the outcome. It's neat, it's clean, it's comforting. But the quantum world? It was a mess. Particles behaved like waves. Electrons didn't orbit neatly like planets. They fuzzed around in clouds of probability. You couldn't say where something was, only the chance of it being there. It was like trying to draw a map of fog, and Bohr wasn't scared of that. He leaned into it. While Einstein kept trying to bring the weirdness back to something familiar, something he could explain, Bohr was saying, "No, this is how the universe works. The weirdness is the point." Bohr had this idea. The reason quantum mechanics seems so strange isn't because the theory is broken. It's because we're trying to ask the wrong kinds of questions. Einstein wanted to know what was really happening inside a particle before we measured it. Like, does the particle have a position before we look? Does it have a definite spin or energy or momentum? Surely it has to, right? But Bohr pushed back hard. He said that asking what something really is before you interact with it doesn't even make sense in the quantum world. In fact, he argued, it's a meaningless question. It's like asking what flavor music is, or what a shadow tastes like. These aren't wrong answers. They're just the wrong type of question. To Bohr, a particle doesn't have definite properties sitting there waiting to be revealed. It doesn't have a spin of up or down before you check. It has all possible spins, or none, until you ask it a specific question. And when you do, the universe gives you an answer. But that answer didn't exist before you asked. It's not that the particle was hiding its state from you. It's that the state didn't exist at all until you made a measurement. That's the heart of what's now called the Copenhagen interpretation, named after the city where Bohr worked. It says, the act of measurement doesn't just discover reality, it creates it. And that's not poetic fluff. That's the actual physics. To make this a little more grounded, imagine you're watching a coin spin in the air. Before it lands, it's flipping too fast to tell whether it's heads or tails. In a classical world, even if you don't know the result, the coin has some value. It's going to land one way or another. It's just your lack of knowledge that's the problem. But in Bohr's view of the quantum world, that coin isn't just unknown, it's undecided. It doesn't exist in a state of heads or tails. It exists in a kind of swirling mix of both. And only the moment you catch it, only the moment you interact with it, does it become one or the other. That was radical, not just to Einstein, but to everyone. Because if that's true, then what we call reality is deeply dependent on what we choose to observe, how we observe it, and when. It means the observer isn't separate from the system. The act of looking changes what's real. And if that's true, then the universe is way more connected, way more interactive, and way more unpredictable than we ever thought. This is also why Bohr rejected the idea of hidden variables, the thing Einstein was holding on to. Bohr thought that adding more layers behind the scenes, extra variables or secret instructions, missed the point entirely. He believed quantum mechanics wasn't incomplete. It was already doing something totally new. It was describing a universe where possibilities are real, not just the outcomes. And he had this wonderfully frustrating way of explaining it. Bohr would say things like, no phenomenon is a phenomenon until it is a measured phenomenon. In plain terms, nothing exists in a measurable way until it's measured. It's not that particles vanish and reappear. It's that reality doesn't take a shape until you ask it to. He also talked a lot about complementarity, one of his favorite ideas. This is the notion that particles can have more than one nature. They can act like particles and waves, but you can't observe both at the same time. What you see depends on how you look. So if you set up an experiment to catch a particle's path, you get a path, but you lose its wave behavior. If you set it up to catch its wave nature, you get that, but not its path. Reality shows you what you're looking for, but never the whole thing at once. To Bohr, this wasn't a glitch. It was a feature. It was a new kind of logic. Not the black and white, yes or no logic we're used to, but a logic of both and. A logic of possibility. A logic where two things can be true, but only from different perspectives. This completely flipped the script, because in classical physics, truth is independent of us. The sun shines whether we look or not. The rock is solid whether we touch it or not. But in Bohr's world, that line gets blurry. And that's exactly what drove Einstein mad. Not just the physics, but the implications. If Bohr was right, then the universe wasn't just unknown. It was unknowable in the way Einstein believed it should be. To Einstein, the whole idea that something could be both here and there until you measure it was nonsense. He famously said, "Do you really believe the moon isn't there when you're not looking at it?" Bohr didn't blink. In fact, if you'd asked him that same question, he probably would have said, "It depends on how you define looking." And this wasn't just intellectual banter. These were the two most important minds in physics, clashing at the very edge of what we could understand. They debated at conferences, they exchanged letters, and each time, Bohr stayed calm, measured, but absolutely firm. Einstein would come up with a new thought experiment, trying to expose the flaws in quantum theory, and Bohr, sometimes overnight, would find a counter-argument using the very same logic Einstein hoped to defeat. Bohr never tried to make the quantum world feel normal. He didn't dress it up in everyday terms. Instead, he insisted that we were the ones who needed to change. Our language, our logic, even our idea of what's real. And weirdly, over time, Bohr's view became the dominant one. Not because it was easy, but because it worked. The Copenhagen interpretation predicted the outcomes of quantum experiments better than anything else. It was messy, yes. It was confusing, absolutely. But it matched reality. The math held. The results were reliable. The theory, as strange as it was, kept proving itself. So while Einstein kept fighting for clarity, Bohr settled into the mystery. He didn't claim to fully understand the quantum world, but he believed that understanding didn't always mean reducing things to parts. Sometimes it meant accepting the whole, especially when the whole refuses to be broken down. And maybe that's why Bohr's view has lasted, because instead of trying to tame the strangeness, he let it be strange. He let it show us that the universe isn't made of things sitting in boxes waiting to be found. It's made of possibilities. And when we ask the right question, reality answers, not with certainty, but with something even more powerful, a truth that depends on how we choose to see it. For decades, the question of whether quantum entanglement was real or just a strange mathematical trick hung in a frustrating stalemate. The equations of quantum mechanics predicted these spooky connections perfectly, but no one could figure out how to test it. It was like trying to prove a ghost exists without ever seeing it. Scientists debated endlessly, trapped in a puzzle with no clear way forward. The math worked either way, and the mystery felt almost philosophical, a question of interpretation rather than experiment. This deadlock left the science community divided. Was the universe fundamentally interconnected in this bizarre way, or was entanglement simply an illusion born from incomplete understanding? It wasn't until 1964 that a brilliant breakthrough shattered this impasse and finally gave the world a way to peek behind the curtain. John Bell's game changer. John Bell was not the loud, charismatic figure you might expect to shake the foundations of physics. He was quiet, thoughtful, and deeply curious. Working at CERN, the sprawling European Nuclear Research Center, Bell didn't set out to become a revolutionary. He simply wanted to understand a puzzle that had haunted physicists for decades: quantum entanglement, that mysterious link between particles that seemed to communicate instantly, defying everything Einstein believed about the speed of light and reality itself. For years, the debate between Einstein and Niels Bohr wasn't just philosophical. It cut to the core of what the universe really was. Einstein, with his famous dismissal of spooky action at a distance, believed in hidden variables, unseen properties that would explain the strange behavior of particles in a way that kept reality local and deterministic. Bohr and his followers embraced the uncertainty and randomness at the heart of quantum mechanics, accepting that particles don't have definite states until measured, and that entanglement was an intrinsic part of the quantum world. But all of this had remained until Bell, a battleground of interpretation. There was no clear way to say who was right, because both sides agreed the differences couldn't be tested directly. It was philosophy masquerading as physics, and frustratingly, the debate raged on. Then Bell designed a mathematical inequality, a clever, elegant formula that would change everything. This inequality wasn't just an abstract equation. It set a clear, testable boundary between two fundamentally different views of reality. If Einstein was right, if the universe was governed by hidden variables, then measurements of entangled particles would always obey certain limits. They would never violate the inequality Bell had written down. But if Bohr and quantum mechanics were right, if entanglement really was this bizarre, non-local phenomenon, then experiments should show violations of Bell's inequality. The particle's behavior would step outside those bounds in ways impossible to explain with classical physics. Suddenly, the debate was no longer stuck in the realm of ideas. It had moved firmly into the realm of experiments. Bell's theorem transformed the question from, "Is entanglement real?" into, "Can we design an experiment to prove it?" It was a breakthrough, not just mathematically, but philosophically and practically. It handed physicists the key to potentially settle one of the biggest arguments in modern science. The power of Bell's theorem was its simplicity and clarity. It wasn't mired in complex quantum math or philosophical jargon. It boiled down the differences between Einstein's worldview and quantum mechanics into something measurable. Bell showed that if the universe obeyed local realism, that nothing could influence anything else faster than light, and particles had predetermined states, then the outcomes of measurements on entangled particles would never break his inequality. But quantum mechanics, with all its weirdness, predicted something extraordinary, a violation of this inequality. If experiments found this violation, it meant the universe did not obey local realism. It meant that entanglement was real, and faster than light influences, or some form of non-local connection, were baked into the fabric of reality. Bell's insight wasn't just a new tool, it was a challenge. Could physicists create an experiment precise enough to test this? The technology and experimental techniques had to be pushed to new limits. For decades, these tests would become a kind of holy grail in physics. When physicists began setting up experiments, they faced enormous hurdles. Entangled particles are fragile and difficult to create in a lab. Measuring them without disturbing the system was another challenge. Plus, they had to close what are called loopholes, alternative explanations that might make the results ambiguous. The experiments had to be airtight to really test Bell's inequality. In the 1970s and 1980s, physicists like Albert Einstein and others pioneered these tests with photons, particles of light. They created entangled photon pairs, sent them through carefully controlled paths, and measured their polarization. These experiments started to show what quantum mechanics predicted: violations of Bell's inequality. This was no longer a theoretical debate. The experimental results were shaking up the foundations of physics. They suggested that nature was more interconnected and less local than anyone had imagined. Bell's theorem had done what few scientific ideas ever do. It had taken an abstract, nearly philosophical problem and made it tangible. It handed scientists a way to probe the very nature of reality itself, and the universe responded with something utterly strange. The implications were profound. If the universe is non-local, then the classical picture of separate, independent objects influencing each other only by local interactions was wrong. Particles, once entangled, remain linked no matter how far apart they travel, with instantaneous correlations that defy our everyday intuition. Einstein's hidden variables, in their simplest local form, couldn't explain these results. Bell's inequality was violated again and again, confirming quantum mechanics and entanglement as real phenomena, not just quirky math or interpretive guesswork. Yet the universe still guards its secrets closely. While Bell's theorem ruled out local hidden variables, it left open the door for other interpretations, like non-local hidden variables or many worlds. But what it made clear was that reality was stranger than Einstein ever imagined. John Bell himself didn't live to see the full impact of his work. He passed away in 1990, quietly respected but without the celebrity his discovery might have earned in another age. But his inequality remains a cornerstone of modern quantum physics, guiding research into quantum information, computing, and cryptography. Today, Bell's theorem is not just a historical milestone, it's a living part of science, underpinning technologies like quantum encryption that promise to revolutionize how we secure information. And it continues to fuel philosophical debates about the nature of reality, causality, and information. What started as a quiet question in a CERN office became a profound turning point. John Bell's game changer wasn't just an equation. It was a doorway, opening onto a universe where connections transcend space and where reality itself is woven from entangled threads, forever challenging our deepest assumptions about the world. First experiments and the shock of violation. In the 1970s, a new chapter in the strange story of quantum entanglement was about to unfold, one that would shake the very foundations of physics. For decades, entanglement had been a theoretical curiosity, something that troubled the great minds like Einstein and Schrödinger, but was difficult to test directly. The question lingered: is quantum entanglement just a mathematical oddity, or does it describe a real, physical phenomenon? This question pushed two physicists, Stuart Friedman and John Clauser, into action. They set out to bring entanglement down from the abstract into the laboratory, where they could measure it, test it, and confront the mystery head-on. Their experiment was not just a technical challenge, it was a bold attempt to peer behind the veil of reality itself. Friedman and Clauser focused on photons, particles of light, because these tiny quanta were perfect messengers for the experiment. When photons are entangled, their properties, such as polarization, are mysteriously linked no matter how far apart they are. The goal was to measure these properties at two different locations and compare the results. But what exactly were they looking for? This is where Bell's theorem enters the picture. Proposed by physicist John Bell in 1964, Bell's theorem provided a way to test the predictions of quantum mechanics against those of classical physics. It established what is now called Bell's inequality, a kind of mathematical boundary that classical physics could not break. If experiments showed a violation of this inequality, it meant that no local, classical explanation could fully account for what was happening. In other words, entanglement was real, and spooky action at a distance was more than just a phrase. Friedman and Clauser designed their apparatus carefully. They created pairs of entangled photons and sent them in opposite directions to two separate detectors. These detectors measured the photon's polarization, a property that describes the direction in which the light waves oscillate. By varying the angle settings of the detectors, they could gather data on how the two photons' polarizations were correlated. The first results were nothing short of astonishing. Friedman and Clauser found that their measurements violated Bell's inequality, just as quantum mechanics predicted. This meant that the entangled photons were connected in a way that defied any classical interpretation. The measurement of one photon's polarization instantly influenced the state of its partner, even when they were separated by a distance that should have made any communication impossible, according to the speed of light limit. For many physicists, this was a shock. Einstein himself had famously dismissed entanglement as spooky action at a distance, believing that there must be some hidden variables, unknown factors, that explain the correlations without breaking the rules of locality. But Friedman and Clauser's experiment left little room for doubt. If hidden variables existed, they could not be local. The universe seemed to behave in ways that challenged our deepest intuitions. Yet despite the excitement, not everyone was convinced. Science thrives on skepticism and rigor, and several doubts remained. Could the experiment be flawed? Were all photons being detected fairly? Could the detectors have biases or inefficiencies that skewed the results? These concerns weren't trivial. In fact, they represented what are known as loopholes in the experiments. One major loophole was the detection loophole, the idea that only a fraction of entangled photons were actually recorded by the detectors. If the missing photons behaved differently from the detected ones, it might explain the apparent violation without requiring spooky physics. Another was the locality loophole. To conclusively rule out any communication between the detectors, measurements needed to be space-like separated, meaning the information couldn't travel from one detector to the other without exceeding the speed of light. If this wasn't ensured, skeptics argued, the results might still be explained by some hidden influence. Despite these loopholes, the Friedman and Clauser experiment marked a turning point. It was the first time anyone had managed to push quantum entanglement out of theory and into empirical reality. It showed, more clearly than ever, that the universe at its smallest scales didn't follow the comforting rules of classical physics. Over the following decades, countless other experiments built on Friedman and Clauser's pioneering work. Physicists worked tirelessly to close loopholes, improve detection efficiencies, and separate detectors by larger distances. With each new experiment, the evidence piled up. Entanglement was not only real, it was a fundamental feature of the quantum world. The implications of this are profound. Quantum entanglement is now recognized as the bedrock of emerging technologies like quantum computing and quantum cryptography. But beyond applications, it forces us to rethink the nature of reality itself. If entangled particles can influence each other instantly across vast distances, what does that say about space, time, and causality? Friedman and Clauser's experiment was a bold leap into this unknown, opening a doorway that physicists are still walking through today. It challenged the classical worldview, proving that the quantum world is stranger, more interconnected, and more mysterious than anyone had dared imagine. It forced the scientific community to grapple with a universe that is deeply entangled and fundamentally non-local. And so, the shock of violation, Bell's inequality broken in the lab, was not just a moment of scientific discovery. It was a moment that redefined our understanding of the very fabric of reality. An aspect in closing the loopholes. In the early 1980s, the question of whether quantum entanglement was a genuine phenomenon or just an odd quirk of theory was still a fierce battleground. The earlier experiments, starting with John Clauser and Stuart Friedman in the 1970s, had already shaken the foundations by showing violations of Bell's inequality. But the skeptics were not convinced. They saw gaps, loopholes, in the experiments that could, in theory, allow for hidden explanations that didn't require abandoning classical intuitions about how the world works. Enter Alain Aspect and his team, based in France. They were determined to push the experiment beyond any shadow of a doubt. Their goal was to close every possible loophole, to design an experiment so airtight that if entanglement failed, it would be because it simply wasn't real. No excuses. One major concern was the locality loophole. In simple terms, this means that when two particles are measured far apart, the measurement on one particle shouldn't be able to influence the other faster than the speed of light, according to Einstein's theory of relativity. But what if somehow, some signal, hidden and sneaky, was slipping between the detectors, influencing outcomes behind the scenes. Maybe the detectors could communicate faster than we think, or some unknown mechanism could coordinate the measurements after they were set, giving the illusion of entanglement. Aspect's team devised an ingenious solution. They made the measurement settings change while the particles were already in flight. Instead of deciding how to measure a particle before it was emitted or while it was traveling, they used fast, automatic switches that could randomly and rapidly alter the measurement settings during the brief time the particles zipped between detectors. This was no small feat. It meant the measurement choice on one side couldn't possibly influence the other, at least not without breaking the universal speed limit set by light. To pull this off, they upgraded every piece of the setup. Their detectors were faster and more sensitive, capable of capturing the subtle quantum effects more reliably. The switching mechanism, controlled by electronic devices, removed any human choice from the equation. No experimenter's bias, no guesswork. Pure automated randomness dictated the measurement parameters. This was essential because human intervention could, in theory, leak some hidden information or open subtle loopholes. The result? Once again, Bell's inequality was violated. This was massive. It meant the weirdness of quantum entanglement was not some experimental fluke or artifact of measurement. The particles' behaviors were genuinely linked in a way that defied classical explanation, even when the settings were changed on the fly, too quickly for any signal to travel between them. Aspect's experiments made the world sit up and take notice. They gave strong evidence that entanglement was real, not just a mathematical trick. Yet even with this breakthrough, the scientific community wasn't unanimous. Some skeptics clung to the idea that maybe, just maybe, there were hidden variables or tiny, undetectable signals that could still explain the correlations without breaking locality or realism. They speculated about influences so subtle and fleeting that no current experiment could catch them, signals hiding at the very edge of physics, slipping through in the last millisecond before measurement, guiding the outcomes in perfect synchrony. So the scientists didn't stop there. They doubled down. If entanglement was real, it needed to be tested in every way imaginable to close these remaining loopholes. They designed experiments that improved timing precision, increased distances between particles, and refined randomization methods. Aspect's work became the foundation for a new era of quantum tests, what we now call loophole-free Bell tests. These experiments aimed to rule out any classical explanation once and for all. The stakes were high. Confirming entanglement meant accepting that the universe behaves in ways fundamentally different from anything we experience in daily life. It meant embracing non-locality, the idea that particles could be connected instantly, regardless of distance, in a mysterious web woven by quantum mechanics. Aspect's experiments were the turning point. They showed the power of careful, creative experimental design to reveal the universe's secrets. They transformed entanglement from a philosophical curiosity into an experimental reality, laying the groundwork for modern quantum technologies like quantum computing and quantum cryptography. In a way, Albert Einstein and his team became quantum detectives, closing doors on every classical escape route and forcing the world to face the strange, beautiful truth of quantum entanglement. Their legacy is a reminder that the universe often defies our expectations, and that science's greatest advances come from daring to test the very limits of what we believe possible. The 2015 loophole-free verdict. For decades, the idea of quantum entanglement sat at the edge of science and philosophy, a puzzle that teased the minds of physicists and philosophers alike. Could two particles, no matter how far apart, instantly influence each other? Einstein famously dismissed it as spooky action at a distance, refusing to accept that something so strange could be real. Yet, the theory of quantum mechanics insisted otherwise. But here's the catch. For years, all experiments testing entanglement had little loopholes, tiny cracks where doubt could creep in. Maybe the detectors were communicating in some hidden way, or the choices of what to measure weren't truly random. These loopholes kept scientists from declaring, with absolute confidence, that entanglement was real. It was like hearing a thrilling story but suspecting a trick behind it. Then, in 2015, everything changed. That year marked a turning point. 3 independent research teams, one in the Netherlands, one in Austria, and another in the United States, simultaneously carried out what are now hailed as the most rigorous and airtight tests ever performed on entanglement. Their experiments weren't just incremental improvements. They were carefully designed masterpieces meant to close every known loophole. Imagine detectors placed so far apart that no signal traveling at the speed of light could connect them in time to influence the measurements. That's what these teams did. This wasn't just about distance, but timing, precision, and absolute randomness. To pick what property to measure on each particle, they used random number generators, genuinely unpredictable machines designed to ensure no hidden pattern could tip the scales. Why was that important? Because if the measurement settings were predictable or could somehow influence each other, the experiment's integrity would crumble. In previous tests, critics could always point to these loopholes to argue that local hidden variables, secret influences confined to the particles and surroundings, might still explain the results. But these 2015 experiments tackled those doubts head-on. Each team independently measured pairs of entangled particles, photons, tiny packets of light, but with a twist. The measurement settings were switched rapidly and unpredictably, while the photons were already in flight, and the detectors were so far apart that any signal trying to influence both would have to travel faster than light, which, according to Einstein's theory of relativity, is impossible. The result? The correlations between the particles' states were just as quantum mechanics predicted, too strong and too perfect to be explained by any classical, local theory. Bell's inequality, a mathematical boundary that local hidden variable theories can't cross, was shattered decisively. This was the loophole-free Bell test, a phrase that sent ripples through the physics community. The long-held suspicion that entanglement was a trick or an incomplete description crumbled. The idea that the universe was strictly local and deterministic, the comforting vision Einstein clung to, was no longer compatible with experimental reality. It was a dramatic shift. Think about it. The universe, at its most fundamental level, refuses to be pinned down by our classical intuitions. It's as if the cosmos itself whispers a secret, that distance and locality, concepts that shape how we experience reality every day, are not fundamental limits in the quantum world. These experiments didn't just confirm entanglement, they transformed it from a curious theoretical prediction into an undeniable feature of reality. Yet the implications go beyond just settling scientific debates. If entanglement is real, and the universe allows these instantaneous connections, it challenges our deepest notions of causality and the flow of information. It forces us to reconsider what reality means. Are particles independent entities, or are they connected parts of a whole, no matter how far apart? In a way, the 2015 loophole-free verdict was not just about physics, it was a philosophical awakening. The 3 teams, working independently across continents, converged on a truth that defied classical logic. Their results were consistent, repeatable, and irrefutable. This was science at its finest, not just pushing boundaries, but breaking through them. By finally closing the loopholes that had plagued previous tests, they made entanglement an unavoidable reality for physicists to grapple with, opening new doors for quantum technologies and deepening the mystery of the quantum world. From quantum computing to ultra-secure communication, entanglement now stands as a cornerstone, powering technologies that once belonged to science fiction. But perhaps most profoundly, it forces us to embrace the universe's stranger side, a realm where connections transcend space, and the fabric of reality is woven with threads that defy the limits of classical physics. In 2015, the verdict was clear. Entanglement was not a trick, not a misunderstanding, not a local hidden variable in disguise. It was real, a fundamental part of the quantum world that continues to inspire wonder, curiosity, and a reimagining of reality itself. Is quantum entanglement real? Once physicists finally stopped debating whether quantum entanglement was real and accepted that particles could indeed remain mysteriously connected across any distance, they began to ask a much bigger question. What can we actually do with this strange, invisible thread linking particles together? What started as a mind-bending oddity of physics quickly turned into one of the most exciting frontiers of modern technology. Entanglement wasn't just a weird phenomenon to marvel at. It was a powerful resource waiting to be harnessed. Imagine the kind of problem computers today struggle with. Tasks so complex that even the fastest supercomputers would take millions of years to solve. These aren't just theoretical challenges. They're real problems in cryptography, materials science, medicine, and beyond. Enter the quantum computer, a device that uses qubits, quantum bits, capable of existing in multiple states simultaneously, and, crucially, becoming entangled with one another. Thanks to entanglement, quantum computers can perform certain calculations exponentially faster than classical computers. This isn't just incremental improvement, it's a fundamental leap. When qubits are entangled, the state of one qubit instantly influences the state of another, regardless of the distance separating them. This allows quantum computers to explore countless possible solutions at once, homing in on answers to problems that would otherwise be hopelessly out of reach. But entanglement's power doesn't stop there. The same spooky connection offers a breakthrough in something just as critical: security. Our world increasingly relies on secure communication, especially over the internet, where data breaches and hacking attempts are constant threats. Quantum entanglement provides a way to create communication channels that are unhackable by any conventional means. Here's how. When two parties share entangled particles, any attempt by an eavesdropper to intercept or measure these particles disturbs their entangled state. This disturbance is instantly detectable by the communicating parties. In other words, entanglement acts like a tamper-proof seal on messages, alerting people the moment someone tries to spy. This principle underlies quantum encryption, which promises to revolutionize privacy and data security in the coming decades. But entanglement goes beyond computation and communication. It even challenges our notions of movement and transfer. Quantum teleportation, a technique that might sound like science fiction, actually uses entanglement to transmit the exact state of a particle from one place to another, without physically moving the particle itself. This doesn't mean teleporting objects like you see in movies. Instead, quantum teleportation is about transferring information about a particle's quantum state with perfect accuracy. By entangling particles between two locations, scientists can recreate a particle's state on the far side instantly, effectively teleporting the information. This could form the backbone of future quantum networks, allowing information to flow securely and instantly over vast distances. These possibilities stayed theoretical for a long time, but in recent years, experimental breakthroughs have catapulted entanglement from the lab to the real world. In 2017, China launched the world's first quantum satellite, NexuSpace, which successfully sent entangled photons across more than 1,200 kilometers between space and Earth. This was a monumental proof of concept, showing that entangled particles could maintain their connection over unprecedented distances, even through the atmosphere and the vacuum of space. This achievement wasn't just a technical milestone. It opened the door to the idea of a global quantum internet, a network of entangled particles linking users anywhere on the planet with unbreakable security. Imagine the implications for everything from military communications to financial transactions to everyday internet use. But entanglement isn't limited to tiny photons or abstract quantum bits. Scientists have pushed the boundaries, managing to entangle increasingly larger and more complex objects. In 2020, experiments successfully entangled visible scale objects, macroscopic objects you could almost see with the naked eye, proving that entanglement isn't just a microscopic curiosity. This brings quantum phenomena closer to the classical world we inhabit and challenges the dividing line between quantum and classical physics. By 2023, physicists reached even further into the quantum zoo, entangling top quarks, some of the heaviest and most unstable particles in existence. These quarks exist for only an instant before decaying into other particles, yet during that fleeting moment, their entangled state persisted. This astonishing feat demonstrates entanglement's robustness even under extreme conditions and on the tiniest scales of matter. What does all this tell us? Entanglement isn't a rare, delicate phenomenon that only shows up under perfect conditions. It's a fundamental feature of the universe, woven into the fabric of reality itself, showing up in particles large and small, stable and fleeting. And we've only just scratched the surface. The applications we know of, quantum computing, secure communication, teleportation of information, are just the beginning. As our understanding deepens and our technology advances, entanglement could reshape the very foundations of how we process information, communicate, and understand the universe. It's not just that entanglement is real, it's everywhere, thriving in systems we've only begun to explore, offering a glimpse into a future where the impossible suddenly becomes possible. Today, we're building quantum computers that run on entangled qubits. These machines don't just solve problems faster, they solve problems in ways classical logic literally can't, like factoring numbers so fast they could crack encryption, or running algorithms that find the right answer by testing every possibility at once, but only picking the best one. Without entanglement, none of it works. We're also using it for quantum encryption, messages that collapse if anyone tries to eavesdrop. We've even teleported information from one particle to another using entangled states. Not matter, not energy, information. And in 2017, a Chinese satellite called NexuSpace sent entangled photons between Earth and space, over 1,200 kilometers, proving entanglement survives even across the vacuum of space. Then in 2020, researchers entangled macroscopic systems, things you can almost see with the naked eye, mirrors, crystals, even clouds of atoms, entangled like ghostly twins. The line between quantum and classical, it's fading fast. So back to the big question, is quantum entanglement even real? Yes, it's been proven again and again in labs, in space, in theory, and in technology. But maybe the better question is, what does real even mean anymore? Because entanglement doesn't work the way we think things should work. It laughs at distance. It ignores time. It suggests that reality, at its core, is not made of things, but of relationships. The world isn't a collection of separate objects. It's a web of invisible connections. And somehow, even when separated by light years, parts of this web still pull on each other. Not through force, not through energy, but through information. The universe, it seems, is not built like a machine. It's more like a song, a pattern, and entanglement is the harmony that holds it together. If this dive into the strange world of quantum entanglement blew your mind, drop a comment below and tell me which part amazed you the most. And if you haven't already, hit like and subscribe so you won't miss our next adventure into the hidden wonders of the universe. Thanks for watching. Stay curious because reality is far more mysterious than it seems.